Hello, everyone. Thank you for joining us today. We'll be presenting to you our project called Feasibility Analysis of Geothermal District Heating for Deneta First Nations. Please meet our team, Ekaterina and Julie Younes from University of Toronto, Serafim Grubas from University of Alberta, and I, Hasmik Asmaryan from the University of Calgary. We will start with an introduction, providing you with more details about our case study, motivation, and objectives, then talk about community modeling, policy analysis, and last but not least, the conclusion and final recommendations. Today, more than ever, we understand how forces beyond our control shape and impact our lives. One of such forces is climate change, which pressures our planet, changing life conditions. The main driver for climate change is burning fossil fuels for our everyday needs, including building heating, in the process releasing heat-trapping gases called greenhouse gas or GHG emissions. These emissions change the temperatures and weather patterns on our planet, leading to irreversible consequences. Transitioning to renewable, affordable, and clean energy production is an urgent priority worldwide. In November last year, at the United Nations 26th Annual Conference of Parties, Canada pledged to reduce emissions by 40 to 45% from 2005 levels by 2030 and achieve net zero emissions by 2050. The pathway to a low-carbon future is through transitioning to renewable energy production with less wasted energy and more energy-efficient buildings. The GHG emissions vary widely across provinces in the country. We decided to focus on Alberta as the province is the highest emitter, with buildings being the second highest emitters after fossil fuel production. Building heating consumes about 80% of energy, emitting about 50% GHGs in the province. Switching to renewable heating is an important step towards a low-carbon energy future. One such energy source is geothermal energy, which is thermal heat derived from the earth. For Alberta, geothermal energy production is a logical fit due to its high potential, oil and gas industry history, similarities in processes, activities, and also talent pool. Well temperature profiles examination show shallow geothermal potential in northwestern Alberta, enough to provide heat and warm water. The picture on this slide shows a well temperature profile from one of the wells in Chateh area. Considering Alberta's geothermal potential and also fossil fuel dependency for building heating in northwestern Alberta's rural communities, we decided to focus on Chateh Township, which is home to the Deneta First Nations. We engage with community to understand if switching to geothermal energy-powered heating system would fit communities' goals and purposes. The project is important for the Deneta community as for the past several decades, forestry and oil and gas industries have accelerated and diversified, experiencing tremendous growth in Deneta people's traditional lands. The figure on the right shows the density of oil and gas wells in Chateh. Despite this industry's rapid growth on the Deneta lands and their consequent substantial contributions to Alberta's economy, based on the documented ethnography, the Deneta First Nation have not received these economic benefits and continue to experience below Canadian average living conditions to date. In recent news, Deneta have been highlighted as they are directly experiencing climate change effects and want to transition to a clean energy economy. The community feels a sense of urgency to protect their traditional lands and sustain their ways of life. We met with community representatives and reviewed Canadian census data. From our conversation with the community representative, we learned that the community members are dealing with high utility costs. Our HOT 2000 simulation showed that the heating demand in Chateh homes is 2 times higher than the national average, with 20% higher heating costs than average Albertan home and 100% higher than average Canadian home. An alternative heating solution is a shallow geothermal district heating network, as this is the resource that community has. In these systems, the central energy stations provide heat directly to buildings through an insulated underground pipe network. The system transmits hot water from the plant to each connecting building, rather than having individual building boiler condenser systems, thereby reducing emissions, maintenance, and replacement costs. Our technical question is how much of the Denetah First Nation community needs will be met through district heating, and can we measure the economic feasibility? The project addresses the United Nations Sustainable Energy Development Goals, including but not limited to climate action, responsible consumption and production, affordable and clean energy, and partnerships for the goals. And with this, I'll pass it to Katya to talk about community modeling.
Thank you, Hasmik. In this next section, I will discuss a possible solution that we created based on our conversation with the Denetah First Nation. To realize an energy partnership, we modeled the community with a proposed district heating design to understand the economic, social, and environmental impacts on the system, on the community, as well as to determine the feasibility of geothermal energy for an energy transition. Over the next few slides, we will take you through our analysis method, where the main steps are, firstly, modeling the community heating demand for all buildings. Secondly, modeling geothermal energy for the community. A techno-economic analysis to assess the project financial viability over its life cycle and quantify risk. And finally, a policy analysis to understand how to move forward and opportunities for collaboration. Firstly, we needed to understand the community heating demand. HOT 2000 from Natural Resources Canada software modeled the community buildings with information about occupancy, building utilization, building construction and age, as well as the area climate. It was important to create the custom simulation of Chateh, as many of the homes were older compared to the Albertan and national averages from census data. The Alberta building codes, in effect from 1974, were used to get an accurate understanding of building envelope materials and construction. We also use census data to get an understanding of occupancy patterns. Often, there is a higher upfront cost associated with renewable energy, and when trying to consider changing the whole demand to sustainable resources, it can put financial burden on the community. To address the community's desire for long-term solution, participation in carbon-free movement is often recommended in tandem with retrofitting existing infrastructure. As we do not know the community's view about retrofitting their buildings, we made a few recommendations, including shallow and deep retrofitting, as well as new build following the R2000 standard for 5th-generation homes. With retrofitting, we found a reduction in both the demand and heat loss. On the chart, energy intensity was found to decrease per meter squared of buildings. Although this is still higher than the Albertan average for retrofitting, this is many gigajoules of demand reduction, making a smaller heating bill for the occupants. As well, this would also reduce the heat loss, which was most significant for homes and would drop from 49 to 10% for new build buildings. To extract geothermal heat from shallow depths, ground source heat pumps will be used. A ground source heat pump mechanically circulates thermally conductive liquid solution through ground loops. After absorbing the ground's thermal energy, that solution then goes back into the heat pump and exchanges its heat energy with a liquid refrigerant inside the heat pump itself. That refrigerant is then turned into a vapor and compressed. The act of compressing that vapor, it increases the temperature. Once that vapor is hot enough, it enters into the heat exchanger, which transfers that heat to the fluid in the district heating network. That warm fluid is then circulated in the network to the buildings and all the homes. Using the specification about the heat pump as input, EPANet software from the Environmental Protection Agency was used to model the district heating system, which included pipe information and placement, as well as specification, including length, diameter, insulation, and friction coefficient. We decided to create 3 separate district heating systems based on the distribution in the community as one possible solution and implementation. These are shown using the 3 colors on our figure. Using EPANet, we were able to find the pressure and velocity at each junction pipeline, and from this, we were able to calculate the temperature at each endpoint directly. Using around 20 vertical wells at 200-meter depth, we found we were able to get a minimum of 23 degrees Celsius across the district heating network, with 26 degrees Celsius from the central station location with the ground source heat pumps, represented by the different colors on our map. We found that our project could meet 70% of the heating demand and offset it to geothermal, which includes 100% of space heating and about 50% of domestic hot water demand. Red Screen software was used to determine the techno-economic analysis of the project. And what Red Screen does is it determines if renewable energy projects make financial sense by analyzing the entire project lifecycle and finding the best technology for the solution. We used it to assess the current community as well as our proposed system. What we found was that the capital cost was $40 million with an 11-year payback time for the district heating system. As the lifespan of the system is 25 to 30 years, towards the end, the municipality would cumulatively have $68 million and be making around $7 million annually towards the end. This calculation included the municipal budget to reduce the equity of the system, but did not include additional funding opportunities from federal and provincial government. We will discuss this in detail towards our conclusion. We also modeled a few alternative solutions using Red Screen, which included the retrofitting and new build. And we found that although the initial capital investment is higher, there would be a greater return on investment and final benefits to the community. Any sustainability project will touch multiple act, regulation, and legislations, and it is important to complete a policy assessment to ensure that the project can be implemented. Our main research question involved an investigation of the regulatory landscape, challenges, and opportunities for project implementation in Alberta. Here, the main policy issue is to examine the involvement of the Deneta and land protections in the current policy. For the analysis, we divided the project into 5 main stages: the drilling and installation stage, land management, environmental assessment, utility provision, and infrastructure establishment. To assess the relevant policies on each stage, we propose metrics based on Sustainable Development Goals developed by United Nations. The first metric, honoring Indigenous way of life and meaningful participation, energy equity, renewability of resources, transition off fossil fuel, life cycle and economic management, energy security and reliability, and environmental protection. This table summarizes our policy analysis for each technical stage against the proposed metrics. We categorize the policies as being fully supportive in green color, a potential risk area in yellow, and high risk in red. High risk areas refer to missing a policy definition which constitutes a gap, or a policy that had implementation barriers for the community. For the environmental protection and energy security, existing policies were found to meet these metrics, seen in green. However, the majority of metrics identify improvements of current policy, shown by yellow. These include many problems with development of a self-reliant community and also incentivizing the transition off carbon. However, we found 3 main areas where current policy needs significant improvements. The first and most important is the inclusivity of the Deneta. The most significant action would be to develop joint stewardship agreements to provide meaningful participation of the Deneta in the decision-making process over their traditional land, and also to ensure fair benefit from the energy industry. The second is that existing infrastructure must be assessed priorly to ensure that the heating utility is affordable for all community members of the Deneta. The last area is safeguarding of geothermal and groundwater resources that are required in the project to ensure that these resources are protected from exhaustion. The solution for this could be better acts definition for renewability requirements. And with this, I pass it on to Hasmik to conclude our project.
Thank you, Katya. A geothermal district heating system is an opportunity for Deneta First Nation to participate in the clean energy sector. Following our analysis, 70% of the area's fossil fuel used for heating was reduced prior to retrofits on the community's original buildings. Emissions were reduced by 33.4 thousand tons, that is equivalent to removing over 6,000 cars off the roads at the cost of 40 million and the average payback period of 11 years. In general, the relevant acts, regulations, and legislations provided clear outlines for municipalities and contractors to begin development and operation work for Alberta municipalities. The project's preliminary study shows that retrofitting is essential to reduce energy demand. However, the economic feasibility is a major barrier to the deployment of the project. The total cost calculated includes transportation costs, licensing, engineering works, and materials. However, developing the district heating can be possible through funding sources such as Deneta's annual budget, the Mackenzie County's annual budget, and grants on retrofitting, making the project economically more accessible. The proposed project can create direct and indirect jobs for the community. Nowadays, the federal government is increasing investments on building retrofits to make homes more energy efficient, such as Canada Greener Homes initiatives that helps homeowners through the accelerated grant payments. The following specific ideas and recommendations for future works are based on the analysis performed on our study. There is future opportunity to investigate combining heat sources into district network, similar to Calgary District Heating Project. Current geothermal maps are built on older information and are hard to find for shallow depth. An understanding of the Deneta First Nations vision on retrofitting initiatives is needed. There is also an opportunity for collaboration between Deneta First Nation and industries. This project is an opportunity for partnership that will address the community's desire for sustainable heat and thermal housing readiness for several generations to come. With the right policies and investments today, the vision of healthy people in healthy places on a healthy planet can be realized. The research was conducted under the NSERC Create Redevelop grant. We are grateful for the opportunity to work on the land on which the universities of Alberta, Calgary, and Toronto operate. We would like to thank the Deneta for their collaboration, openness, and sharing their knowledge and experiences with our team. We would also like to thank Redevelop program leadership and all the mentors for their valuable advice and direction while conducting the research. Thank you.